All right, class, let's continue evaluating more limits of functions, and let's see if we can make it faster this time. So we've learned we could make tables of values, graph the function, or simply evaluate if we can. So this is going to be really our method or our first idea. If we want to find a limit, let's see if we could just plug in the value, and if we can, then what happens again at a point is what happens really near the point. So if we can plug in the value, that means there's really not anything funny going on possibly. Okay, so we'll see. So here it is. Can I just simply plug in a 2? 5 times 2 over 2 minus 6, that's going to be a 10 divided by negative 4. So there you go. The answer is negative 2.5. Done. Just as simple as that. I'm going to use a different pen. Okay. Now, can I plug in a 2 right away? As you see, right, and I'm not even going to waste my time. If I plug in a 2, 2 minus 2 would be a 0 at the bottom, so that just doesn't work. Now, can I factor out the top? And by the way, notation-wise, you are not allowed to drop the limit symbol until you're ready to plug in the value. So why did I have to write the limit here? Because I'm still supposed to evaluate this expression and plug in a 2. Why did I not write it here anymore? Because I'm already evaluating the limit. I'm done. What does it mean to find a limit? It means to plug in the value of 2. Yes? So that's what we did, right? Now, of course, the limit means to look at what happens around, but how do we find the limit? By plugging in the value. And if we get a nice answer, then we should be safe. Okay, so again, remember, this is a limit, so x is really not equal to 2. So 2 minus 2 is really not going to be equal to 0. That means we can divide the x minus 2 expression part, okay? And now I can plug in 2, and I'm dropping that limit symbol, right? And I'm going to get a 4 for an answer. All right. So let's see. Can I plug in a 0 into this limit right here? The answer is no, because 4 divided by 0 is undefined. Now, could I factor this and then reduce just like up above? The answer is no. There's nothing to factor in 4 and there's nothing to reduce. So the only thing we get to do is make a table of values and see what happens. So if evaluating doesn't work, then fine, let's plug in some numbers. So supposed to look at what happens near 0. Well, 0.1 is near 0, 0.01 is near 0, 0.001 is near 0, yes? Getting closer and closer and closer to 0. So if 4 divided by 0.1 is 40, 0.01 is 400, 0.0001 is 4,000. So what you're really doing is just adding on another 0 to your answers. Now we have to look from both sides. Okay, so we have to make 2 tables of values, as I said, because we have to look from both sides. Okay, so coming from the left-hand side with lesser values than 0, what am I going to get? Well, negative 40, negative 400, and negative 4,000, and so on and so on. So the closer I get to 0, what's going to happen to these values? What are they merging to? What are they getting closer to? Well, the next one's going to be 40,000 and 400,000 and 4 million. And so I'm not getting close to a value and then stopping there, right? So the more 0.00000s I put, the larger and larger and larger values I'm getting. So really what happens here is that we're getting infinitely large values. So this is what we would call, not necessarily an infinite limit, but this limit gets closer to infinity. The problem is, on the other side, I'm going to get negative infinitely large values. So it's not that I can even commit to one side of infinity. So what I'm going to also do for you is graph this function. If you remember from your college algebra classes, this is a rational function, or also called, specifically this one, the reciprocal function. So 1 over x has this graph. 4 over x is the 1 over x graph stretched vertically by a factor of 4. So it's going to go up much faster, but it's really doing this. So it's the 1 over x function stretched up by a factor of 4. So that's the idea of what this graph is going to look like. So as you see, what happens to this graph as x gets closer and closer to 0? Well, if I getting closer and closer to the 0 from the right-hand side, yes, with larger values than 0, so positive, yes. This is going to get more and more and more and more towards the infinity, yes. Infinitely large values. There's no end to that. The same thing happens on the left-hand side, except for the closer I get to 0, right? The y values get closer and closer to what? To negative infinity. So they get negative infinitely large. So what's going to be then our answer? Our answer is that there is no limit. Okay? Even if we should say infinity, okay, if let's say both of them were going up, yes? Infinity is not a number. So we can say the limit equals to infinity. By this we say the values, the emerging values are larger and larger and larger from both sides, yes? But infinity is not a value, so the limit still does not exist. So when you say a limit equals to infinity, what we're saying is that the y values get as large as you want them to be. So arbitrarily large, that's what we say. All right, I got one more for you. So here it is. And can we plug in a 0 for h? The answer is no, because you're going to get a 0 on the bottom, so you can't evaluate it. Well, can we factor this one maybe first? Oops, h, not x. Can we factor up the numerator? Sure enough, there's a greatest common factor of h in both those terms. So, by the way, if you want to review anything for the beginning of this course and for later on as well, factoring is a big one. Factoring will really set you off a little bit. I mean, it's just going to put you ahead. If you don't know how to factor, then you're going to have a hard time with many of these problems. Okay, so review factoring, if anything. If you're wondering what to do, that's what you should do. So we can cross out the h's. So I'll get a limit as h approaches 0 of h minus 4. And when I plug in a 0 for h, I'm just going to get a negative 4 for an answer. All right? And there is that. Okay. So as we already saw many times, it just kind of helped to look at one-sided limits. Even this problem right here, coming in from the right-hand side, the values were approaching positive infinity. Coming in from the left-hand side, the values were approaching negative infinity, yes? So maybe sometimes we're like, okay, the limit does not exist, but at least what we could say, hey, if you're coming, the limit from the right was infinity, the limit from the left was negative infinity. So I'm bringing back this graph from before. And what we were interested in is what happens at this value here. The limits exist, right? The double-sided, coming in from left and right, we were approaching 2. Coming in from left, coming in from right, both sides were approaching the value 3. Coming in from left, coming in from right, we're approaching the value 1. But here we had a whole gap in the function, right? A whole jump in the function. So how do we write this? So the limit as x approaches 4, it was different coming in from the left than coming in from the right. So what we're doing is we're putting a little minus sign, and we're going to review this on the next page. So as x approaches 4, with a little minus simply means that we are coming in from the left-hand side, so with values less than 4. Okay. of f of x. So what happens with this function is I'm only getting close to 4 with lesser values, right? So before 4. So clearly, if I'm only looking at this one-sided limit, the y values are getting closer and closer to 2. Okay. What's the limit as x approaches 4 from the right? So we put a little plus sign there. So the little plus sign simply means the x's are greater than 4. Okay. So if I'm coming in with greater than values than 4, right? Closer and closer, what's the y value that they are approaching? That would be a 3. Okay. So the left-hand limit is one thing, the right-hand limit is one thing. When they are not the same, definitely we cannot commit to one value. When you put 4 only, yes, means from both sides. So the left-hand limit, yes, is one number. The right-hand limit, yes, is one number. But the double-sided limit is no value at all. Okay, and just to practice on this, let's just pick one more. What is the limit coming in, let's say, at 3 from the left? So getting close to 3 from the left-hand side, right? Smaller and smaller values, I'm going to get close to 1. What is the limit as x approaches 3 from the right? So I'm getting close to 3 from the right. So I'm coming this way. Then the y values are still getting close to 1. Yes? So what that simply means is if you're coming and the left-hand limit is equal to the right-hand limit, then the double-sided limit, it does exist and it equals to 1. Okay. All right. So let's review the definition right here. So the left limit as x approaches c of f of x is L, that's how we would read it in words, if the values of f of x get close to L, as we want, as close to L as we want, when x is very close and to the left of c, in other words, lesser values, and that's how we write that. Okay, so as x approaches c from the left, we put a minus sign, means with lesser values, yes. If the y values get as close as we want them to be, yes, to this L. So look at that. I was coming in here to x approaches 2 from the left, yes. So what do I mean? I can make them as close as I want to 7. By getting as close as I can to 2. So can I get even closer to 7? Sure. All I have to do is pick a 1.999999, and then I'm going to get even closer to 7. Yes, so that's what it means. Is you're not going to stay too far. You can push and push and push closer and closer and closer to 7 by pushing the values closer and closer to 2. All right. And the same thing, the right limit, as x approaches c of f of x is L, right? If the values of f of x get as close as we want to L, when x is very close to and to the right of c. So, and then we put a plus sign, means we're looking at the right-hand limit only. Okay? And now this is the important part that I said. If both the left limit and the right limit exist, in other words, infinity is not a choice. Yes, so when I said the limit equals to infinity, it doesn't mean it exists. We're just saying it gets infinitely large. So if both the left-hand limit and the right limit exist, or their value, and they're equal to the same value, right? So the same number L, then when we say the limit, also sometimes called the double-sided limit, will exist and equal to the same value. So what does this mean again? This means one more time that if what? The limit as x approaches some value c from the left is L, and the limit as x approaches c from the right of f of x is also L, then we can conclude from both that the limit as x approaches c, period, means you could put like a plus and minus if you want. That means from both sides is also L. So that's exactly what we figured out here, right? Maybe I should have waited to write the definitions first. You see the left-hand limit is not equal to the right-hand limit. That means what? They're not the same, so the double-sided limit doesn't exist. Whereas here, coming in from the left and coming in from the right, we're approaching the same value, yes? So that means the double-sided limit without the plus or minus, right? Means from both sides is equal to that same number. Okay, so when do we get gaps like this in the graphs? It's kind of funny, but when would this happen? For the most part, they happen with what we call piecewise defined functions. So a function that looks one way on one side and one way on another. We looked at a function like this in the first part of the video. This is what the graph of a piecewise defined function would look like, where this is really a reciprocal function and this is a radical function. So it's two different functions on different parts of the number lines. And that's when they might not be connected, right? So where one lives off, the other one picks up somewhere else. So definitely this is a good graph where the right-hand limit will not equal to the left-hand limit. Yes. By the way, what's the right-hand limit just by looking at the graph? As I get closer and closer to 0, the y values get closer and closer to 0 as well. But if we're looking at the left-hand limit, right, coming in from the left, as x gets closer and closer to 0, what do the y values get closer and closer to? Well, that'd be negative infinity, yes, so it's not even a value. Okay. All right, so how would I do that without, I don't want to graph this. Okay, so let's find a whole bunch of limits. Now, as you see, the definition for this function is changing when x is equal to 2. So you have one definition for this function for x is less than 2, and one definition for this function for x is greater than 2. Okay, so what does it mean to find the limit as x approaches 2 from the left, right? So one more time, that means the values of x have to be less than 2, okay? So, well, if the values of x have to be less than 2, that means I am supposed to pick this side of the definition, right? Because that's what the function equals to when x's are less than 2. So I'm supposed to find the limit as x approaches 2 from the left of, I have to use this part of the definition. Okay? So plugging in a 2 here, that's going to get me an 11, right? Okay. What is the limit as x approaches 2 with a plus? 2 with a plus simply means that the x values have to be greater than 2, yes? If it's greater than 2, then this is the definition that I'm supposed to use. So what's the limit as x approaches 2 from the right? And I'm supposed to use x plus x squared because that's what the function equals to for larger values than 2. So 2 plus 4 is 6. Okay, so the left-hand limit equals to 11. The right-hand limit equals to the 6. So what's going to be the limit as x approaches 2, period? What do you think? Well, if you wrote does not exist, then you would be correct. Why? Because this only exists if coming in from the left is the same thing if you're merging onto the same value from both sides. You can't be merging towards 11 coming in from here and towards 6 coming in from here. That means what? There's a gap in the function, yes? All right. I'm asking you all the same questions about 0. Okay. So this is going to be a little bit tricky. And the reason why this is going to be a little bit tricky is because, let's see if you know which part of the definition you're going to have to use. Well, x x approaching 0 means which definition do I have to use? X is less than 0. If you're less than 0, you're definitely less than 2, yes? So this is the part of the definition that we have to use. So go away, ant. It's too hot. Okay, so plugging in a 0, you're going to get a 1. Okay. Now, what am I going to use on this side? X gets close to 0. That means x is greater than 0. So which part of the definition for this function do I use? So I'm getting closer and closer to 0, but with larger values than 0. So where am I in this definition? Now, if you pick 5x plus 1, you would be correct. So why are we still picking 5x plus 1? Because you're looking at a limit, right? So what does it mean we're looking at a limit? Wherever this graph might be, right? Fine, it's going to be something up to 2, and it's going to be something else after 2, some kind of quadratic function, yes? So the point is, yes, at 2, exactly I switch definitions, right? Less than 2, greater than 2, close to 2 is clear. But when you're close to 0, when I'm looking at a limit, right, what kind of values are we plugging in? Values as close as possible to 0. So if you're going to put in values that are as close as possible to 0, even if you plug in, what does it mean approaching 0 from the right? Means you're going to plug in 0.1, 0.01, 0.0001. All of these are values less than 2, yes? When I'm getting close to 0, I don't pick 3, 4, 5, and 7. Those are not values close to 0. And again, think about your tables. What kind of numbers, again, you plug in? Something super, 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 super close to 0, yes? Positive, or this one coming in from the left means I'm plugging in negative, the same values, yes? So the point is, being close to 0, either way you look at it, you are still way less than 2. Yes, so you're using that part of the definition. So for every of these x values you're plugging in, all those x values are less than 2. Okay, so that's still going to be close to 1. So what's the limit from both sides? 1. Why? Because the left-hand limit at 0 is equal to the right-hand limit at 0. They both equal to the same number, so the limit exists. Okay, so again, I hope this is clear what one-sided limits are and how they help us figuring out what happens to a certain graph. So I can tell for sure there's a gap in the graph when x is 2. I can tell for sure that at 0 the graph goes right nicely through, and it goes through a y of 1, by the way. Okay, and the last task for this section, maybe we can finish it on this video, so I don't have to start a new one. Trying to always limit or keep the videos at under half an hour. Okay, that takes less to upload them, and you guys get less tired of watching it. Okay, continuity. What does it mean for a function to be continuous? Well, clearly, we already talked about it a little bit, and what we said is that a function really is continuous if what? If the graph goes right through. So in other words, in layman's terms, a function is continuous if we can draw the graph without lifting the pen from the paper. That's the layman's terms. Without lifting the pen from the paper. In other words, there are no gaps, no holes, no gaps, no jumps. Okay, nothing. All right, so you can draw that graph right through without making a fuss. Okay, so when you look at this graph right here, where are the discontinuities? So where is the function not continuous? Also called discontinuous. So this function is going to be discontinuous at what? X equals to what? Where do you see a hole or a jump? I see a hole at x equals to 2. I see a hole at x equals to 3. And I see a hole at x equals to 4. Okay. So, in other words, I go right through, yes, and then I have to jump. Here, there's a hole I have to jump, bubble this in, continue, stop, bubble this in, continue over here, right? So anytime we have to lift the pen from the paper to be able to continue drawing this graph, the function is discontinuous at those points. Okay, so we're going to come back to this page, but I want to talk about what's the proper definition of continuity. Okay, so a function is continuous at a point. So as you saw, this function was discontinuous before at what? X equals to 2, 3, and 4, yes? It's discontinuous at these points, but that doesn't mean it's not continuous throughout. It's continuous at 2.2, it's continuous at 2.5, it's continuous at 3.3, it's continuous at 4.1, right? It's continuous everywhere except for these 3 points is where I had to stop in my graph. Okay, so a function is continuous at a point if and only if the limit at that point equals to the function value at the point. So in other words, what this really means is simply what? What happens near an x value, that's the limit, right? What happens near is the same as what happens at the point. At the value. Okay. So that's the definition of continuity. In other words, the proper definition actually has 3 parts, so if you were in calculus, you'd be bothered a lot with proof continuity using the 3-part definition. Okay, so I'm just going to tell you what it is. So the 3-part definition says, as you see, that the limit has to exist. In other words, the limit as x approaches a of f of x is some value, right? To exist means it's some number, right? The function value at x equals to a exists. So in other words, the function is defined at a. You can plug in a into the function, right? There's no hole there, so you have a function value and you get a number, right? And the third part is that the 2 of them are one and the same, so you get the same number, right? So the limit as x approaches a is the same number you got when you plugged in a into the function, right? They're both equal to the same value, okay? All right, so just to recap this, and then we will continue. We'll do a couple more examples. A function is said to be continuous, period, right, on its whole domain if it's continuous at every point in its domain. So continuous means nowhere throughout have you had a hole or a gap. So a function is continuous if there was no gap, no hole or jump on its whole domain. Okay, so you went right through nicely from beginning to the end. Okay.